Hi, I'm Mr. Miller, and this is a lesson on inverse of a relation. So the inverse of a function is a relation that maps the range of a function back onto its domain. Now, some simple examples of that. If you have a function that multiplies by 2, then the inverse is dividing by 2. If a function is adding 1 to a number, then the inverse is taking away 1. Where it gets a little bit more tricky is with an example like this, where there are two operations, multiplying by 2 and adding 1, what would the inverse be? So in this question, we want to determine the equation of the inverse. We want to graph the original function and its inverse and do a comparison. So let's take a look at one method for doing that. So I'm going to refer to the original y equals 2x plus 1 as the original f at x. That's the original function. One method for finding the inverse is to consider what's done to x in the original function and undo what was done in reverse order. So here's how that would go. The y equals 2x is multiplying by 2 and adding 1 in that order. So to undo it in reverse, you subtract 1, then divide by 2, which means the equation would go y equals x minus 1, then divided by 2. If we simplify, not simplify, but put it into a different form, y equals a half x minus a half. And I suggest that you put it into this form because at this point, most people can recognize this is the y-intercept, this is the slope, and it would make graphing easier for some people. So let's get to the graphing. We've got a grid here that goes from -10 to 10, both in x and in y. I'm going to graph the blue or original function first, the y equals 2x plus 1. It has a y-intercept of 1 and a slope of 2, so I can easily get my points here. Y-intercept is 1, slope is 2, so up 2 over 1, up 2 over 1, and so on. And I can connect all those points together with a nice straight line, and I can label that y equals f at x. Next, I'm going to graph the one in red. So as I mentioned, this is the y-intercept, it's -1/2. The slope here is 1/2, which means you go up 1, right 2 to get to other points. And you can continue on in that direction, connect all your points together with a nice straight line, put arrows on the ends, and I will get to labeling that in a moment. So what you may notice at this point is that the red graph is a reflection of the blue graph across the line y equals x. Every single point that is on the blue graph, if you go to the purple line, and then you go across the purple line to the same distance away, you'll have a corresponding point. So this point was the point 0, 1. This reflection is the point 1, 0. Notice the x and y coordinates are switched. Here's another example. You've got a point 1, 3. And if you do a reflection across the line y equals x, you get the point 3, 1. Which means a second method for finding the equation of the inverse would be, starting with the original function, if you had it as f at x, to write it as y equals, to switch the x and y, and then to solve that equation for y. So subtracting 1 from both sides, dividing both sides by 2, you get y equals a half x minus a half, which is what we had before. Now you can replace the y with this f inverse notation. And this is the inverse. Now you should really only use this f inverse notation if the inverse is actually a function. Now for those of you who are not sure about it, let me just tell you that yes, the red graph is a function, and the reason I know is because if you draw a vertical line and you take that vertical line and you sweep it across the entire grid, you'll notice that that vertical line only crosses the red graph at most once. If it crosses more than once, then it's not a function. It is a relationship, but it's not a function. So since this red graph is a function, we can use the F inverse notation, and now I'm going to use that as my label. This is y equals F inverse of x. Next, we're going to determine the equation of the inverse of y equals x squared, and we're going to graph y equals x squared and its inverse on the grid to the left. We're going to do some comparison. Then we're going to look at doing some restrictions on the domain of y equals x squared so that the inverse is also a function. So here's y equals x squared. As you should know, the vertex is at 0, 0, and it opens up from there. We connect all the points together with a nice smooth curve and label it y equals x squared. This is our original function. Now, in order to come up with a graph of the inverse, we could just take every point and switch the x and y coordinates. So for instance, 0, 0 becomes 0, 0. 1, 1 becomes 1, 1. 2, 4 would become 4, 2. 3, 9 goes to 9, 3, and so on. So let's take a look at the rest of the points. Here's another point. We started with negative 1, 1, and we switched to 1, negative 1. Negative 2, 4, switched to 4, negative 2. Negative 3, 9, switched to 9, negative 3. So now I'm going to connect these points together with a nice smooth curve, put arrows on the ends. And this is y equals plus or minus the square root of x. Now, this is a function, the blue one. The red one is not a function, and it's because it fails a vertical line test. If I draw a vertical line at any point here, it would cross the graph in 2 places. The only exception is right at the vertex, or where the function is undefined, but in lots of other places you can see that I'm crossing over 2 times. So here's that reflecting line y equals x. And we would say that the red graph is the blue one reflected in the line y equals x. The invariant points on this transformation are 0, 0, and 1, 1. Notice that when we do a reflection across a line, the invariant points are the points on that line. So 0, 0, and 1, 1 are the 2 points on that line. Now what I'm going to do is I'm going to restrict the domain of y equals x squared to just being x greater than or equal to 0. In other words, I'm going to leave off the left branch. When I take all of these points on here and I switch their x and y coordinates, what I get is this. And it's only y equals the positive square root of x. So this is actually a function now. And again, it's a reflection in that line y equals x. So here's the summary. You can graph the inverse of a relation from the graph of the original relation by switching the x and y coordinates of every point on the original relation. The graph of the inverse of a relation is the graph of the original relation reflected in the line y equals x. The domain and range of the inverse are the range and domain of the original function, and that's respectively. So the domain becomes the range. If it's x is any real number, then for the inverse, it's y is any real number. And if the original function has a range of y greater than or equal to 0, then for the inverse, it'll be x greater than or equal to 0. The horizontal line test is where you move a horizontal line through the entire range of the original function. And if it passes through the graph at most once, then the original function has an inverse that will also be a function. Otherwise, this will not be the case. To get the equation of the inverse from the original relation, what you can do is switch x and y and solve for y. You can create an inverse that is a function that doesn't pass the horizontal line test by restricting the domain of the original function so that it passes the horizontal line test. And when the inverse of a function is also a function, then the inverse is denoted by this F inverse notation. Thanks for watching this lesson and have a great day.